Hi everyone, I'm Praneeth from Mechanical Regular second year. So today I'll talk about inductance. So what does the word induce mean? Induce means to bring about or give rise to. So what does this word mean in the context of electricity? Let's see. Basically, in electricity, current and magnetic fields, these two quantities usually are induced. Like if there is one quantity, there will be an induced quantity. Like if current is there, a changing current is there, magnetic field will be induced. If the changing magnetic field is there, current will be induced. So basically, this phenomena has been observed. It has been observed that when there is an electric current flowing in a conductor, there would be a magnetic field around the conductor and vice versa. So basically, if there is a current flowing in a conductor and there is changing current flowing through it, a magnetic field will be generated around it. So basically, uh, if we have a conductor and current is flowing through it in a specific direction, and the current is changing with time, there will be a magnetic field around it. The direction of this magnetic field with respect to the direction of current can be determined using the right hand thumb rule. Point your thumb towards the current direction and curl your fingers around the conductor. The direction of these curling fingers gives us the direction of the magnetic field, as you can see in the diagram. So, once this phenomena has been observed, there were scientists trying to formulate this phenomena. First comes Faraday. He gave the Faraday's law of electromagnetism. So, basically, he observed that whenever there is a changing magnetic flux and a conductor near it, there is an EMF generated in the conductor. EMF means electromotive force, or simply we can say it's a voltage. Basically, if there is a changing magnetic flux near a conductor, there will be voltage developed in the conductor. So Faraday was able to give the equation for the EMF. He according to him, the magnitude of the EMF generated in the current conductor is equal to the changing flux or rate of change of flux near the conductor. This is Faraday's law. Then came Lenz. So in Faraday's law, we got to know the direction of whatever the induced EMF is. I mean, we got to know the magnitude of the induced EMF. So when there is an EMF, there will be current. So what is the direction of this current? This is given by Lenz law. Lenz law states that the direction of the electric current induced in a conductor by changing magnetic field is such that the magnetic field created by the induced current opposes the change in the initial magnetic field. Basically, when there is a changing flux, there will be a current induced in a conductor, and this induced current creates a magnetic field, and this magnetic field is such that it opposes whatever the phenomena the initial magnetic field is creating. Lenz law is very useful when determining the direction of induced current and induced EMF. So we can see a few cases here. When there is no relative motion between the conductor and the magnet, there is no change in flux, so no induced flux, no induced current, or no induced magnetic fields. When there is an increasing current, I mean increasing magnetic field, there's a current, and this current is creating another magnetic field which opposes the initial magnetic field. And there's a decreasing magnetic flux, so the conductor creates a supporting magnetic field. This is actually opposing the idea of dying magnetic field. Uh, in the concept of induced quantities, they always oppose whatever is happening. So similarly, these two cases. So once we got to know what basically inductance is, like when there is a conductor, there's a current in it, and the current is flowing through it. and there is a rate of current, a magnetic field is generated around it, and this magnetic field gives you another mag current which opposites the initial direction. So basically, we got to know what inductance is. So we needed, scientists have developed a device called inductor. This might be the simplest uh, electrical component in terms of design. It's basically a wrapped wire. So you take a soft iron core and start wrapping a wire around it, and boom, we have the inductor. This might be the simplest electrical device. So as you can see in the diagram, a wire is wrapped around a soft iron core, and when there is a changing current in this wire, there will be magnetic field that is generated around it, and basically the energy is stored as magnetic fields, and this magnetic field gives rise to EMF, and that EMF provides you induced currents and stuff. So what exactly is inductance? Inductance is the tendency of an electrical conductor to oppose a change in the electric current flowing through it. The changing electric current produces a magnetic field around the conductor. This magnetic field induces a current opposing the changing current. The basic reason for inductance is change in magnetic flux. So now we got a device called inductor, and we know what inductance is. There should be a measurement for it. Like we should be able to quantify it. So to quantify it, we have measurement of inductance. In SI units, inductance is measured in Henry's H. Now we know how a basic inductor looks like. It's basically a solenoid. Solenoid means a coiled wire wrapped around a soft iron core. So the inductance can be given by, inductance is represented by the letter L, and L on the coil is given by mu r mu naught n square A by L, where A is the area of cross section of the inductor. So basically, L is the inductance in Henrys, mu r is the relative permeability, and mu naught is the permeability of free space, which is 4 pi into 10 to the power minus 7 Henry per meter. And N is the number of turns or number of times the wire is wrapped around. A is the coil area, R is the radius, and L is the coil length. So this is basically the formula we use to determine the inductance of a given solenoid. And there are a few more related quantities to an inductor. The induced EMF due to a varying current passing through it. This is what we seen in the, this is uh, similar to what we have seen in the Faraday's law. The induced EMF is given by L into minus di by dt. This minus just represents that the induced EMF is opposite to the direction of whatever the original current is. And we already talked about the energy being stored as magnetic field in the inductor, and this internal energy U is given by Li square by 2, where L is the inductance, I is the current passing through the inductor. Yeah, and inductor reactance in AC circuits. This is something new. Basically, in DC circuits, we have a quantity called resistance. The equivalent resistance offered by inductors, capacitors, and these things in AC circuits are called reactance. It is represented by XL for inductive reactance. It is given by omega L. Omega is the frequency of the AC, like whatever the frequency by which the AC signal keeps on changing, and L is the inductance of the given inductor. So now if we start connecting inductors in DC circuits, there's nothing much that we can observe. Like once the current starts current reaches the steady state, inductor is basically a short circuit. When the switch is just turned on, inductor opposes the growing current in the circuit until the steady state is achieved. Once the steady state is achieved, the inductor acts like a short circuit. When the switch is just turned off, the inductor will not let the current suddenly reach zero. It opposes the decaying current by inducing a current to enlarge it. So basically, if you look at a circuit, it's a RL circuit. There's a battery and the current is flowing in this direction. When you just switch it on, the current starts rising from zero until it reaches the steady state. So the inductor starts opposing that growing current. When the switch is just turned off, then we have a decaying current. So the inductor won't let the decaying current, like it won't let the current go down. It starts supporting it. So often the inductance is also called electrical inertia because of this phenomena. Like it doesn't stop immediately, like it has some inertia. So also if we have multiple inductors, these are the formulas to be used. Like if the inductors are connected in parallel, 1 by L equivalent is given by 1 by L1 plus L, 1 by L2 plus 1 by, and so on up to 1 by Ln. And if they are in series, we can just add the inductance. There are a few examples, I mean, applications of inductors, like the choke coils, transformers. Inductors are used in motors, inductors are used in LCR circuits, radios, filter circuit, induction stoves, relays, etc. So that's it for that's the basics of inductors, and thank you for watching.